12:35. So if you're just sitting back down, welcome back. I'm going to go ahead and get started. So similar to how Richard presented this morning, we're going to sort of alternate back and forth between a couple slides that sort of gives an overview and motivates ourselves, and then do some interactive work as well. And so I'm going to go ahead and start sharing my screen. And everyone should be able to see my slides, yes. Okay. All right, so let me make sure I have the chat up here so I can see. Okay, great. All right, so yeah, so we're going to continue talking about ESPEI. So what Richard talked about before, obviously, is PyCalFed, and so that is the our tool for doing forward CalFed type simulations. So you have a database that contains Gibbs energies or contains some other properties that you have modeled, and you can go ahead and do forward simulations with that. And so what ESPEI tries to do, and what we're going to talk about for the rest of today's workshop, is how you go in reverse. So how you go from data and how you generate a database that you can then use to do forward simulations. And so some of these slides I have here, Zikoi covered a little bit, so I won't dwell too much on them, but the idea here is that what we want to do is model the Gibbs energies into individual phases, and model different parts of the Gibbs energy, so the surface of reference, configurational ideal entropy, other physical models, and then excess terms for the parts that we don't have any physical or other derived terms for. And the way that we typically do that is by combining the derivatives of the Gibbs energy in terms of data and phase boundary, phase equilibrium data in order to fit these functions. And then, like I mentioned, we do forward simulations with those Gibbs energy functions and understand materials and material properties. And we do this typically in CalFed by building up databases from pure elements to binary, ternary, and multi-component. And so if you're familiar at all with CalFed, you know that there's a wealth of commercial databases out in the on the world that you can purchase. And a lot of these databases traditionally have been developed for particular alloy systems. So I have a case on the left here that plots the isothermal section of nickel, titanium, iron from a commercial database and from a open database in the literature that reassessed the entire system over the entire composition and temperature space. And so what you can see here, if we just look at comparing these two, is that the phase stability in the right-hand diagram from the literature does not agree with the commercial database. And so we can see that there are some ways that we can improve these large multi-component databases that are often designed around a particular alloy system. One other challenge that we have in CalFed is that whenever we have a thermodynamic database, that really only provides a point estimate of our current understanding of the system. And so here I have a figure from a chrome nickel vanadium assessment with some experimental data plotted on top. And we can see that the phase boundary here between the single phase BCC region and the two-phase BCC and Lattice chrome 2 titanium region here is sort of in the middle of these two of these sets of experiments where we found single phase BCC in the stars and two-phase in these cross circles. And so what the data is telling us here is actually that this phase boundary can be anywhere between these two points. There are these sets of points, but we don't actually know for sure where that boundary is. And in the assessment here, they chose to model between them using this data and certainly some other underlying thermochemical data. But we can see that we're even not capturing some of the behavior here as you decrease the vanadium content, and experimentally we saw single phase BCC chrome vanadium titanium. And so if someone were to go use this database then without having this experimental data here, they would not capture the actual understanding of the system, and they may do some alloy design that isn't captured well by this database. And so there's a huge gap here for being able to express to people who consume CalFAD databases about what our actual understanding is. And so these are the problems we'll try and address here, and ESPEI, we think, is tailored very well to solve. And so we've seen this picture already, but just for a reminder, if we imagine we're starting with a large 6-component database here, and we need to change component C because we find out that maybe we want to change the model, or there's something incorrect, or there's new data that requires us to reevaluate this. The amount of work we have to do in our larger multi-component system to change, to accommodate that change of element C grows exponentially as we increase the order of systems that are modeled. And again, as Zique discussed earlier, this can be challenging and problematic because there's all these steps by the time you actually use this 6-component database, all this information that is lost along the way that needs to be recaptured every time someone new wants to reassess a particular portion of this system. And so taking out these metadata and information losing steps, and also reducing the tedium of doing this is also another goal that we're trying to address. And so that brings us to ESPEI. And so initially we had some work published in 2010 where we sort of took an initial stab at this problem using and first presented ESPEI to the literature. And so at this time, we were a little bit limited in the forward simulation software that we used to be able to do these, and this wasn't, it turned out, very practical. And so since then, and as you may have suspected, we have developed PyCalFAD, which is our new underlying thermodynamic engine for doing these forward simulations so that we can make predictions based on a set of parameters, and then determine what set of parameters gives us the best fit, and so on. And so as you saw in many of these examples earlier today, and hopefully can come to appreciate the power and flexibility of PyCalFAD as a library to do thermodynamic calculations. So since then, we've developed a new version of ESPEI. And so the idea here is threefold. So we want to first rapidly generate models from single phase data. So we want to do some initial parameterization. And then, as I mentioned, we want to optimize all these parameters and take out a lot of the tedium of doing this modeling. And also, as part of that, do some uncertainty quantification, where we can try and communicate to our users what the uncertainty in our thermodynamic databases are. And so in this first part here, I want to talk about how we do this rapid model generation from single phase data. And so conceptually, it's fairly straightforward. So we start off with some data about the Gibbs energy and its derivatives as a function of temperature, pressure, and the internal degrees of freedom. And so this can come from, as we discussed yesterday, DFT or other ab initio methods like MD. And we can use this to then take this data, collect it, in particular, collect the derivatives of the Gibbs energy, so the enthalpy, entropy, and heat capacity with respect to some reference states, either formation, mixing, or some other more complicated reference state. And then we want to parameterize them in a typical CalFAD way. And so typically, just looking at temperature alone, we parameterize them according to this polynomial. So we have some a plus bt plus ct log t, and then we have some additional coefficients where t is raised to a power. So maybe t to the -1 or t squared, and so on. And so if we just naively apply this to a set of Gibbs energy data or data that have all the derivatives, we might vastly overfit our Gibbs energies. So maybe we'll fit 5 or 6 coefficients to fit the data exactly. But of course, as many of us know, that having a more complex model leads to overfitting and can lead to poor predictions and poor extrapolations. And so to address that, what we do is when we do this fitting, we use the corrected Akiki information criterion. And so that is this equation here. And so that's expressed as 2 times the likelihood or the model score L. So that's the goodness of fit that you would normally calculate. And then there's these 2 penalty terms here. And this is where the power of this method really is expressed. So typically, if we're only parameterizing according to the model score, we're going to follow this blue curve, and we're going to maximize this likelihood. But as I mentioned, we want to avoid over parameterizing where the data might not support it, and then we have these additional penalty terms here. And so the 2 key pieces that we consider is k, and so k is the number of model coefficients, the model parameters. And so on this diagram, that's the model complexity here. And then so if we just consider this 2 log L minus 2k, that is the Akiki information criterion. And then the corrected version that we use gives us this additional term here. And so this term has an additional penalty. If you have a small number of data points, then the denominator, of course, will be smaller here, and we'll have a larger penalty when we have a small number of data points for having complex models. And so what that will give us, again, referring back to this figure up here, is instead of maximizing the model score with the model complexity, we'll have some trade-off between how good our fit is, and how complex our model is. And so the best model then is the one that maximizes this corrected Akiki information criterion score. And so this is the core principle behind the parameter selection. And so I can show now some interactive demo of what that looks like in practice. Okay. So if you're all following along, we're going to be in the ESPEI folder in the workshop.
The screen is not visible yet, Brandon.
Oh, sorry. Thanks for letting me know.
Of course.
Okay, great. So we should all see my Jupyter lab. And again, let me make sure I can see the chat easily. Great. So if we're in the workshop folder and ESPEI, we'll have 2 notebooks here that we'll work out of today. And so the first one we'll work out of is the parameter selection notebook. And so before we get started, I do want to mention that we also have ESPEI documented at espei.org. And so if you follow that link, you can find our documentation website where we talk about some of the details and history of ESPEI, as well as how to install, how to get started, the change log, so you can see when we've updated. We have a text forum tutorial here for copper magnesium, as well as several how-to examples, different code recipes that we'll talk about some today, as well as detailed reference for all the input files and everything you can do. So that's all here at espei.org. And then all of these, as I mentioned earlier, all of these notebooks come pre-solved, if you will. And so after the workshop, they can be accessed at this GitHub repository here that I think was shared in the chat earlier as well. So I'm going to go ahead and clear the output. so we can at least visibly start fresh, and all the code will be here. And so in ESPEI, again, this is our assessment tool that uses PyCalFed as the underlying engine. You really need three things to get started. And so first, you need a description of the phases that you want to assess. You need a collection of JSON formatted thermodynamic data, which we'll talk about what those look like a little bit. And then you need a YAML file that actually tells ESPEI what needs to be fit, what to run, and allows you to tune the hyperparameters, which we'll also talk about. And so, so I'll go and talk about each of these briefly before we actually start diving into code. And so again, I tried to sprinkle some links to the documentation where these are all documented in detail, where you can read at your own pace. But the phases.json file is the conventional name that I use for this, although you can name it anything you want, and you'll see why that is later. But we have to specify a couple key things. We have to specify which chemical species we're interested in fitting, as well as what phases we're interested in fitting. And then for each phase, we need to specify the CalFed sublattice model. And so if you're familiar with the compound energy formalism, this here is where you define what that is. And so today we're only going to look at chrome nickel, and because it's simple. And I should mention that we have much more complicated examples and wide support for really anything that you can define within the compound energy formalism. And so as I mentioned on the ESPEI website, we have an example for copper magnesium available, which has stoichiometric compounds, phases that have multiple sublattices with different species mixing into those sublattices. And we also support beyond binary, so you can work on arbitrary multi-component systems. And there are even some examples about ESPEI being used for multi-component systems in the literature as well to modify existing databases. But as I said, we're going to keep it simple here just so that everything is approachable, and we don't have to worry too much about modeling details. Okay, so we described the sublattice models, and then we also have to define the sublattice site ratios. And so these are the stoichiometric coefficients that go along with each sublattice. And so in this case, we need to have one coefficient for every sublattice, but again, all these phases have only one sublattice, and so we just use a site ratio of 1 for all of them. And then you'll also notice that we have these aliases here, and these are optional depending on how you name your phases. And so the aliases will allow you to look up data that's called BCC-A2 and then be able to associate that with the BCC phase. And so you can name your phases whatever you want here, and then you can have aliases set up so that if you have heterogeneous data sources, or you want to connect with different unary reference states that might use different phase names, you can do all that as well, and then preserve nice human readable phase names as you desire. So that's the phase descriptions file. And then sort of the most important piece is the JSON files that collect all the data. And so as many of you who may have done a CalFed assessment before probably know, collecting the data is the critical step in any CalFed assessment. If you're familiar with the phrase garbage in, garbage out, this is where you control whether or not your input is garbage or whether or not your input is going to give you good results. And so this is really the key step. And so I have two types of data sets here that are examples of what we're going to use today. Although ESPEI can take in many different types of data. In particular, what we want to talk about is equilibrium thermochemical data. So this being like equilibrium experimental enthalpies of formation or activities, that sort of thing. But like I said, today we won't use those directly at all. And so there's two types that we will use today. So there's this non-equilibrium thermochemical data and phase boundary data. And so for non-equilibrium thermochemical data, the differentiator here between non-equilibrium and equilibrium is that we assume that for non-equilibrium thermochemical data that we know all the internal degrees of freedom exactly. And so for a phase that has one sublattice, there can only be, if you know the composition, you also know the internal degrees of freedom. But for a phase that has two sublattices or more, or has more complex internal degrees of freedom, just knowing the composition is not enough to know the internal degrees of freedom on its own. And you can sort of probe this experimentally, but I think we've had the most success, and it's most convenient to get this non-equilibrium thermochemical data from atomistic simulations. And this is really where the power of ESPEI comes from, is being able to map these atomistic simulations where you can control completely the internal degrees of freedom of complicated phases, and then calculate their thermodynamic properties. So in this case, the enthalpy of formation. And this is what allows you to do very quick and easy parameterizations. And so for this data set here, this is an example of one in our data set today. The key aspects here are that we define these sublattice configurations. And so each configuration here, there's 4 of them, describes what species are active in a sublattice. And so in all of these, we have both species active on each sublattice. And then the occupancies correspond to those as well. And that determines the compositions. And so these are the compositions from this data set. And then we have the corresponding conditions. So in this case, just 1 pressure and 1 temperature for these measurements. And then we have the values. And so these are the numbers associated with the output. So in this case, we have HM form, which is the molar enthalpy of formation. And so these are the values that correspond to these configurations. And so you'll notice that for the values, there's 3 brackets around here, and it's actually a 3-dimensional array. And so what's happening here is that you can describe these thermochemical data using multiple. So if you have a grid of configurations and pressures and temperatures, you can express that entire grid in site fraction, pressure, temperature space using the 3 dimensions here. So the outermost dimension is pressure, and then the middle dimension is temperature. And then the inner dimension obviously is configurations. And so this array is a 1 by 1 by 4, which corresponds to, again, the 1 pressure by 1 temperature by 4 configurations. And so this is the simplest case, and you can imagine more complicated ones. For example, if you were to ingest Gibbs energies as a function of temperature and pressure from and composition from something like pi iron, as we explored a little bit yesterday. The other key type of data that we're going to use today is phase boundary data. And so the way we encode this is by the 0 phase fraction lines, or the 0 phase fraction points. And so in a binary system, these are the tie line vertices. And as you go up into multi-component systems, they still are the vertices of now the tie hyperplanes. And so similarly, we can express these as grids of pressure and temperature. But in this case, we only have just 4 temperatures and 1 pressure. And so we're describing here in the phases which phases do participate in these data sets. And then we have the phase name that participates in this equilibrium. So I've sort of split it up here. So every line is 1 independent equilibrium. And so there's 5 independent ones, which again correspond to the 5 temperatures. And so it's happening.
Brandon,
Yep.
we got a question in the chat here. They commented that they saw that the sublattice occupancies for chrome nickel, just above the phase boundary data, you had some duplicate occupancies. Can you explain what that means?
Yeah, so the reason they're duplicated is just because experimentally they took 2 measurements at the same composition, maybe 2 different experimental runs of the same composition. And so that's where those come from. Thanks for the question. I also see another question in the chat is whether pop files can be imported into ESPEI and whether there's a translator available. As of now, there's no direct translator available for existing pop files. We have a prototype that works for some subsets of data, so like thermochemical, equilibrium thermochemical data in particular, so activities or equilibrium, enthalpies of mixing or formation. That should work. But again, this is really at like a prototype stage right now. And I think the standard is to collect these JSON files and put the metadata in there. As if you worked with a pop file, you'll know that the quality of the metadata in the pop file is really dependent on the person compiling it. And it's really difficult, in my opinion, to take someone else's pop file and try to modify it and use it yourself, because often there's just not enough metadata to be able to track down exactly what they mean. Whereas in comparison, the JSON files, you can put these comments anywhere, and so or have as many of them as you like, as well as we encourage people to link back to references. And I typically have this reference name here, and then we'll link that up with a BibTeX file that has all the metadata for that reference in there, just as convention. And then we have one more thing in the chat here about whether this is a composition set for one sublattice model, but for measurements. That's correct. So FCC, we're modeling with just one sublattice. And so there are 4 different independent measurements here. And 2 of them, we just happen to have 2 pairs of compositions. But there are 4 independent measurements. Okay. So yeah, back to the phase boundary data. So we'll have one, so the way I have it set up here is like I said, there are 5 temperatures and 5 phase boundaries in this data set that we have recorded. And so I've visually split that up onto one equilibria for each line. And so just to be able to bookkeep it and easily visually reference it. And so what each line then means is you have one single equilibria. So this is an experiment where someone maybe made an equilibrated alloy and then quenched it and looked at the compositions, or a alloy of a certain composition and heated it up in the DSC and then noticed a transition temperature, let's say for this composition at 1073 Kelvin. And they recorded the composition of chrome where FCC was the zero phase, has zero phase fraction at that temperature. And so you'll notice that the other side of all of these, the other side of equilibrium, so we have 2 phases in equilibrium, FCC and BCC, and we know the composition for FCC chrome or for chromium in FCC, but we don't know the composition of nickel or chrome in BCC actually. And so we list that as null. So again, just visually, the idea here is that if you imagine a typical DSC measurement, if you make an alloy with this composition and heat it up, you'll see a transition temperature or a transition where FCC appears at 1073 Kelvin. And it's in equilibrium with BCC, but just from that experiment alone, we don't know the composition of BCC. We just happen to know that that is the phase that's in equilibrium with. And so that's the purpose of null here. And so if you did have an experiment where you knew the composition of both phases, you could enter the compositions here. Just checking it, chat here. Okay. So we can see here again, we have these 5 equilibria where we call these like half tie lines. So you know which phases they are, but you only know the composition of one of them. And so especially in binary alloy systems, these are very common measurements. And so we do support this type of data. Okay. So again, I think the chat also is discussing this as well, but I want to continue to emphasize that really the experimental and data collection is really the most critical part of making a good assessment in any software, not only ESPEI, but in any tool you're using to make CalFET assessments. Really, the data is the star. Okay, and the last thing is, as I mentioned, you'll need a YAML file. And so these are human readable key value files that really just describe to ESPEI what needs to be run. And so this is the most simple one that you can come up with for doing a parameter generation sort of activity. And so really the only things that you need to define are what type of excess model you use. So linear right now is the only one that we support, but this parameter is here. So if you wanted to modify ESPEI to support like an exponential excess model, for instance, you could absolutely do that. And then you can also enter the reference state. And so built into ESPEI, we have the SGT 91 papers reference state built in. So all the unaries in this input file will come from SGT 91. But we also have support for adding your own reference states to ESPEI quite easily. And we have had people do this in the past and other activities going on in the future. And so you can pull reference states for unaries if you want, but you can also not include your own unaries if you had that data. So that's all things that you can do with ESPEI. So now we're going to get to the actual code side. And so the idea, as I mentioned, alluded to a little bit before, is that really for us, PyCalFET is the library. So it's the piece of software that gives you all the tools and lays them out in front of you, and doesn't necessarily hold your hand as much, but really lets you really dive in and be extremely flexible and do any kind of calculation you want. Whereas ESPEI, on the other hand, we see as more close to an application. So really, we're going to see a lot of this run ESPEI function. And all we need to do is in this function, we pass it a dictionary of settings. And so if I go ahead and run these imports and open this YAML file that is included for you in the notebook examples, I can also open them and show you just what they look like. So this is the one that we're loading. Again, it's the same information as above in the notebook, and you could also edit these in Jupyter Lab and save it and rerun it, and your changes will take effect. And so after we run the cell where we load that YAML file, we can look at this generate param settings and see that it's just a dictionary of these key value pairs. Yes, Ursula also pointed out in the chat that there are many parameters that have been revised since 1991. I believe we use only the SGT 1991, but I'll have to check on that, what version of the unary we use, because I believe 5 is readily available now of the SGT unaries. But again, if you want to bring your own, if you want to bring the SGT unary 5 database, you are absolutely able to do that with ESPEI. Okay. So now that we've loaded this settings dictionary, all we have to do is run it. And so if we run this cell, we can start to get output according to the verbosity that we chose. So we chose the medium verbosity option. And so it will fit all the phases that we selected in our phase data, our phase JSON file. So BCC FCC liquid, and it finished. And you can see that this ran in like less than a couple seconds. So I could run it again, and we can see it takes maybe 10 seconds maximum to generate these parameters. And so this is really the power of using this non-equilibrium thermochemical data, is that we can directly fit and parameterize very, very quickly. And so now that we have that, we can plot the binary phase diagram and just see, based on the input thermochemical data that we started with, we can see the phase diagram that we get. And so here's the phase diagram, but of course, it's difficult to judge, maybe unless you know the system very well, how good of a fit this actually is, or how good of a parameterization this actually is, unless we compare it to the phase boundary data. And so what we can do is we can use ESPEI and load our data sets programmatically. And then we can use those and do the same binary phase diagram plot in PyCalFed, but then also do this data plot convenience function here in ESPEI. And so you can see that that data plot does not actually use the database object that we created in the parameter generation step. All it requires is the information about the components, phases, and conditions that we're searching over, and then the data sets. And so now you can see that it plotted the data sets on top of the same axes that we got back from PyCalFed's bin plot. And so yeah, we can see that the fit is okay here. Definitely not publication quality, but again, this was parameterized in about 5 seconds using only a limited set of thermodynamic data. And so you can imagine you can easily generate some parameterization like this and generate some CalFed thermodynamic database that you can write out to a TDB file in just a couple of seconds given data. But of course now, as modelers, we want to dive into this and understand what parameters were generated and what we might need to do as we move forward in ESPEI and try to refit and update the parameters that were selected. And so ESPEI provides this plot parameters function that will plot different phases and interactions that you can select. So again, here we only have one sublattice, so these interactions will be simple. But you can also plot, using this plot parameters, different end members if you have them and have data to compare to. Or you can plot, if you have phases with multiple sublattices, you can plot interactions across sublattices or interactions where another sublattice is occupied with one species or another. Again, so we're being able to plot this entire space of the internal degrees of freedom. And so you can see here that in the data we started with, again, now we can visually see these Watson 1995 measurements where we have 2 measurements at the same composition. And so this one is for BCC, and we can see the parameters generated here. That again, this is back to that optimum trade-off between the goodness of fit and the Akiki information criterion penalty for increasing the number of parameters. So we can do the same for FCC and do the same for liquid. And so here are the 3 different, the 3 sets of excess parameters and fits we generated for these different, these 3 different phases. And so this is sort of a qualitative view, but if we actually want to look deeper into what the actual values are quantitatively, we can search the parameters. And Richard showed this actually in the viscosity model, and we're using that same technique here to search the parameters in the generated database. And so here we're searching for all excess type parameters, so that's parameter type L, for the liquid phase, and we can see that we have 3 different order excess parameters. So we have a parameter, excess parameter with order 0, we have an excess parameter with order 1, and we have an excess parameter of order 2 for these 3 different chrome-nickel mixing interactions. And so then for each of them, you can see parameter is what actually has the symbolic expression for what the fitting of this is. And so we have this VV0015, VV0014 times T. And so this is the actual symbolic expression for this interaction parameter. But of course, if we're actually trying to see what happened, these are not very informative because they're just names. And so if we want to look up what those names are, those are all in the symbols dictionary of the database object. And so we can go and look up symbols as a dictionary and pull out what the values are for VV0015 and 0014. And if we do that, we can print out the values and just see that the values that were generated for this zero order interaction are these. But one thing that you might have noticed is that the data here for the liquid phase is strongly only on the nickel side, and there's some disagreement, but yet we fit three orders of interaction parameters, 0, 1, and 2. And so if you have some CalFat experience, you might have thought to yourself, wow, that's a lot of parameters for this phase, especially if we don't even know what the chrome-rich side looks like. And so one of the powerful parts of ESPEI is that you can use hyperparameters to influence the fitting based on your expertise, your modeling expertise. So again, if we plot the liquid here, we might think that using our human intuition and the scatter in this data, especially as we go to the chrome-rich side where there is no data, that we might not need three orders of interaction parameters. And so one example of a way you can influence it is you can apply this Aicc penalty factor. So what this is a additional factor, an additional penalty multiplication factor on that Aicc penalty. And so if you increase this penalty factor, you can influence the Aicc best fit to have fewer parameters because you're increasing that penalty. And you can do the same thing the other way. You can decrease it and then influence more to get more degrees of freedom. And maybe you want that if you have very sparse data, but you know from some intuition that you're going to need that to adjust the energies in the future. And so if we do that, we have another YAML file that is the exact same thing as what's here. And so the only thing we've done is we've changed the database that's output, the TDB file that's output, and we've changed and we've added this Aicc penalty factor for the liquid phase. And so we've set the penalty factor to 10 for each enthalpy and entropy data. And so if we go ahead and load this dictionary again of settings, and then run the fitting again, we can see that it will just as quickly go and do it. And then we can check the number of parameters that were generated. And now we can see that if we run that same search over the new database, we can see that only one excess parameter was generated, modeled as A plus BT. And thanks for checking on that, Richard, on the SGTE5. Okay. And so now if we replot that again, so now again, this is just using zeroth order action. That just visually inspecting it, the fit looks qualitatively almost the same, and then we can just easily pair these two. So our original database and now our new Aicc penalty databases, just in one line and in two different plots or in one cell. And then these should plot in just a few seconds here. Great. And so we can see just visually, these are just from the phase diagram alone, almost imperceptibly different. They're very, very similar. But still, obviously, we can see that there's some room and some, some room to improve and agree with the phase boundary data again, which does not fit here. We're only fitting to this non-equilibrium thermochemical data. And so fitting to all the possible data is where ESPEI's MCMC fitting comes in. And on the interest of time, I'm just going to go ahead and move along to the slides to talk a little bit about MCMC, and then you can do these short little challenges at your own pace. And again, feel free to ask us any questions that you might have. Okay, so we talked about parameter selection, and so now I want to talk about doing this automated optimization of this parameterization to the phase diagram data. And so for this, we use the Markov chain Monte Carlo method, which is a method for Bayesian parameter estimation. And the idea here, the intuition, is that we're trying to fit this posterior distribution, which is the probability of our parameters theta with respect to some data d, or conditioned on some data d. And to calculate that, we multiply the likelihood, so the probability of observing some data given some set of parameters times the prior, which is our current belief, or our initial belief about the probability distributions of the parameter, and then those are all normalized by what's called the data d, which is the probability distribution of the data itself. And so just if you're not familiar with MCMC, sort of intuitively what that looks like for this two parameter system, theta 1, theta 2, as we have this contour plot of different probabilities here, and then the 3D plot on the left. And so this might be our prior. So in this example, we are pretty uninformative, and we're guessing that that theta 1 and theta 2 are not correlated with each other, and are centrally distributed about 0.5 for both of them. But let's say now that we've collected some data and we can evaluate the likelihood of observing that data. And so the likelihood that we computed is here. And so now that we've observed some data and computed the likelihood, we see that actually there is some correlation between theta 1 and theta 2, and the area of maximum probability is not where our prior was in the center, but actually more skewed towards high values of theta 1 and low values of theta 2. And so then if we want to calculate the posterior, we can multiply those together. And typically, and so you can see in the posterior that we've sort of blended together our prior and likelihood. And so we're sort of in between them. And you'll notice that in this picture, there's not this data. And so typically these posterior probability distributions are taken as a proportionality, because the probability of observing any piece of data is often difficult to calculate numerically. So the way we do this in practice, we evaluate this, is by Markov chain Monte Carlo. And so Markov chain is just building arrays, or building a set of values that are all independent from each other. So taking independent samples of theta 1 and theta 2, and then we do that independent sampling by the Monte Carlo method. And so as we build up this Markov chain, we select and accept the parameters that get added to the chain in such a way that the likelihood of any particular pair of parameters, let's say theta 1 is 0.5 and theta 2 is 0.5, the likelihood of those being the values is proportional to how many times they appear in the Markov chain. So at this 50-50 composition, or 50-50 parameter values, that value will occur less frequently in the Markov chain, and something closer to about 0.8 theta 1 and 0.3 theta 2. Okay, and so so one thing, again, if you're familiar with CalFed, that you probably know or may have even guessed based on what we've seen so far, is that CalFed parameters are often correlated. So what this is a corner plot. And so along the diagonal, we see the probability distributions for some sets of parameters. So this one is the A0, this is the B0. And so I've annotated these by the real CalFed coefficients, where we model each excess parameter of order nu here. So 0 is an L0 term, and then we have an A constant plus B times T term. And so again, we see that for this A0 and B0 term, so under the diagonal are the correlations between any two parameters. And so we can see very clearly here that A0 and B0 are highly correlated. And that shouldn't be a surprise to us as CalFed modelers, because if you imagine that you have one correct Gibbs energy that is going to give you a most optimal fit, then there's an infinite combination along this line of A plus BT that's going to give you that exact same Gibbs energy. No matter what A is, you can always choose a B that gives that energy. And so that's where this correlation comes from. And so we can even see as we go into higher order parameters, so an A1 and B1 term, there's also some correlation, but it's a little softer. And these corner plots are good for visualizing this. But often these kind of correlations are very difficult in a traditional Markov chain Monte Carlo method, because if we imagine taking this probability distribution for two different parameters, so in this case x1 and x2, and we're just trying to start at this blue point and then randomly sample the next point that could go in the Markov chain. We might choose something out here, or we might choose something out here. But obviously we see that both of those are going to be in very low probability space, whereas really we want to be sampling in the higher probability space so that we can use our independent samples efficiently. And so what we do for this is use an Ensemble Markup chain Monte Carlo method. And so what this does is we use many what are called chains of parameters simultaneously. And so these chains will sort of map out to what this distribution looks like. And so then when we take a new step, we can scale our new step with respect to the state of all the other chains when we go to take that step. And the property of this ensemble method that gives us this behavior is called affine invariance. So we're just invariant to any affine transformations which are scaling and translation. And so that's how we go about addressing this problem. And so we have a paper from 2019 where we applied this to copper magnesium. So again, we've started here on the left with a single phase data start point, and here's the phase diagram to compare it to. And then we do our Markup chain Monte Carlo method where we have this burn-in phase where we're improving the parameterization, and we're increasing the likelihood. So this is the negative likelihood, so I could plot it on a log scale, but we're increasing the log likelihood. And then you have this uncertainty quantification phase. And so if we apply that to copper magnesium, we can get this phase diagram that is in very good agreement with the experiment. Okay, so now I can spend some time to demo this. Okay, so now we're going to work in the other notebook, so the MCMC notebook. And so these two notebooks are entirely uncoupled, and so you can run them separately from each other. So I'm going to shut down the other one. Okay, and so I talked about all the data and all that stuff already. And so all the data remains the same. You still need this phases.json file that describes what phases that we're going to be fitting to. And the only thing different here is now instead of having this generate parameters option in our file, we now have this MCMC tag. And at bare minimum, to run MCMC, all you need to define are the number of iterations and then the database that you're going to start with. So maybe we would have started with the Aicc penalty one that we generated in the last step. And so this would be all you need at minimum to run a simulation. Then by default, what will happen is it will try to parallelize everything over the number of cores you have on your computer using a Python package called Dask that's developed externally, which is very powerful. But here again, because we're using these cloud resources, and there are 80 or so of us, we want to run it in parallel. And so I have some options here that will just keep it nice and quick. And so for this case, we're going to start with just 3 iterations. Where set the scheduler to none, which means don't parallelize. Otherwise, you would use Dask and specify the number of cores if you wanted to do a certain number of cores. And that can all these settings are all described in the documentation. So if you follow this link, you can read at your own pace all the options that there are for MCMC and the system output and also the parameter generation. You can see them all. And so the only other thing I've set here that I haven't talked about is the output. So I've set the trace file, prob file to both null, so they won't be saved as files. And then I've also set the log file to null so that we can see them be plotted in the notebook. or we can see the output in the notebook. So again, we're going to do the same imports, and we're going to import this MCMC settings file, which is again the exact same as the one that's here. So I won't show you that. But again, it's in the repository, and you're able to do this yourself. And then so then we can run it. I can also clear the output as well, just to make it clean. Okay, so run the import and the load, and then we'll run the MCMC sampler. And so you'll notice this takes a little bit more time, and I can use that time to sort of explain the output that we're seeing here at this verbosity level. So the key thing actually I want to emphasize is that from our parameter generation, we only got off the database from this run ESPEI. But when we do Markov chain Monte Carlo, we get the database, which is our best fit given these run settings. And then we also get this sampler object, which comes from the MC package, which is what implements the Ensemble Markov chain Monte Carlo sampler that we use. And so again, walking through some of this output, we have some information about it's loading the data sets, it's checking or setting up the scheduler if there is one to set up. This time we're not. And then it's saying that we've found 12 degrees of freedom in the database, and so these come from the symbols that start with VV and some number. So those are degrees of freedom. And so if you are trying to do more advanced things, you can control the degrees of freedom by how the symbols are named. So changing their names, you can like fix degrees of freedom, or you can add new ones if you want as well, or control anything you like. And then it's going to build the phase models, start to calculate the likelihood. And so first we do the likelihood of an initial set of parameters. And so at this verbosity level, every time we calculate the likelihood, we get some output. So we get the amount of time that it takes. And then in our 3 categories of data, it'll tell you what the likelihood of each, the log likelihood of each are. And so we have non-equilibrium thermochemical data, which I talked about. We have the likelihood of equilibrium thermochemical data, which is 0 because there is none, as I mentioned for the system and what we're working on today. And then we have the zero phase fraction, or the phase boundary data likelihood. And we also broke out activity, which we just have some special handling for compared to equilibrium thermochemical data. And so so then it calculates the total likelihood of this. And so this likelihood is multiplied by your prior internally. And so for this one, actually, we are not using a prior which is an improper prior is what that's called. But just again, for the simplest case and have reasonable defaults, that's what we chose to do. You can also set up your priors in a variety of ways, and we have a syntax for doing that in the YAML file, which you can read about in the documentation. So then after it calculates the likelihood for the initial set of parameters, it starts to do the sampling. And so by default, one of the options you can set is the number of chains per parameter. So I mentioned for the ensemble method that we have an ensemble of chains which sample the parameter space. And then we are able to scale our new proposals by the state of all the other chains. And so you always need an even number because it does it in batches. So it does the first half of proposals and then the second half of proposals. And it sort of does this A-B, step, 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 step. And so this always needs to be an even number. And of course, the smallest even number you can pick as the default is 2. And so we have 12 parameters with 2 chains per parameter. And so then we initialize 24 chains. And so to do each iteration then, we set it up to do 3 iterations. And so to do one MCMC iteration, you have to calculate the likelihood for all of your chains. And then you can advance to the next Markup chain Monte Carlo step. And so what you see here in the output is here we're calculating the likelihood for every chain 1 line at a time. And so here you can see the breakdown of the prior, the calculated likelihood, and the total log probability, where these are just summed. And so we can see again the output. So there's going to be 24 of these proposals and likelihood pairs. and then we can decide whether we can accept or reject the parameters. And so in this Ensemble Markov chain Monte Carlo method, we use the same acceptance criterion as sort of vanilla Markov chain Monte Carlo, which is the Metropolis Hastings criterion. And so here we decide whether to accept that or not after we've done all the sampling. And that's one iteration. And then we do another iteration and another iteration, and that's our 3. And then at the end, it will tell you what or every iteration, it will tell you what the acceptance ratios are for each chain. And then it will tell you that the MCMC is finished. Here are the initial parameters that you started with. Here are the optimal ones. So the ones that had the highest log probability, and then or the highest probability. And then it will tell you just the change in parameters, which is kind of useful to see how far your best solutions are from your initial solution. And so as I mentioned, the core here is that we get this sampler object back. And this is what actually contains all of these samples of the chains. And so we call that the trace. And it also contains the log probability. And so these are all arrays. And so if we look at just the shape of these arrays, the trace is going to be 24, so the number of chains that we have. Remember 2 times 12. And then the number of iterations, which is 3. And then we need values, of course, for every parameter for each of those iterations for each of those chains. And so we have an array of 24 by 3 by 12. And so we can just sort of inspect that really quick and convince ourselves that that is what it looks like. And indeed, it's a big array that has 3 dimensions. And so this first one here is one chain's worth of parameters. So there are 12 parameters here, and then this will be the second chain, and so on. And then the log probability has a similar shape, except the log probability is 1 per chain per iteration, and so you don't need an additional parameters dimension. So it's just a 24 by 3. Okay. And so now we want to see, even with our 3 iterations, what happened to the phase diagram. And so if we load up our data again so we can compare. So this is this now includes data from all the 0 phase fraction data, so all the phase boundary data, but also the underlying thermochemical data. So any data that you have, the Markup chain Monte Carlo can fit that. And so here, after just 3 iterations, is what we got. And so if we go back to compare to our parameter selection, we can see that the final diagram looks something like this, because remember, after we reduced the parameterization, it was almost the same. And so we can see that the BCC solubility was very low in our initial parameterization compared to the data. But even just running 3 iterations, we've pulled in that, or we've increased the solubility of BCC significantly. And this took, again, about probably 3 minutes on one core, with each of our 3 times 24 samples taking about 2/3 of a second. So it's about 3 minutes. And this is the phase diagram we got. But of course, again, we're running on computational infrastructure. Or actually, let's compare and see what happened to the BCC parameters. So on the top, here's the parameterization that we started with for BCC, and then after, again, just 3 iterations, we have adjusted and made BCC relatively more stable, and we can see that just by comparing visually to the data. Okay, so as I was beginning to mention, is that we're, of course, on cloud infrastructure, and we have limited ability to run full-fledged simulations, and we also have limited time. So typically, again, I showed 3 iterations. Fully converged MCMC simulations can be a few hundred to a few thousand calculations, depending on how, or depending on how complex the system is and how many parameters you have. And so, I went ahead and pre-calculated 2,000 iterations, again, of these 24 chains for a total of 48,000 samples. And so I did this on my laptop. And over 6 cores, it took about 3.5 hours to run these 48,000 samples. compared to the 72 that we ran in just a few minutes here. And so if we look now at these arrays, so ESPEI, we can again, as I mentioned, save out these trace and log prob files. And so I have provided those for you in the notebooks. So you can see that these .mpy, so numpy files, are saved, and we can load them. And then I have this truncate arrays function, which is a useful little utility function that will allow you to use these more effectively. So actually, when you're running your simulation, you can have it save out every number of steps. So like every step, you can save out what the current trace and log probability are. And then the rest of if you've done 10 steps out of 2000, then the rest of the 2000, except for the first 10, will be padded out with zeros. And so what this truncate arrays does is removes all the zeros so that you can do reasonable analysis. And so if we just look at how the probability converges over our iterations as we approach 2000 iterations, we can look and look at the convergence. And so here it's a little difficult to see in the top one, but there's multiple lines, and there's one line for every chain where we have followed that chain through each iteration and probability. And then I've zoomed in here on the bottom, and we can see as we get closer and closer to converged, how the convergence and the probability continues to increase as we get closer and closer and have more and more iterations. And so now if we use this again to and see what other things we can visualize, we can also look at how a particular parameter, so one of those VV0015, for example, changed over the course of the simulation. So we can see here at 0 and very low iterations, we probably started at about 12,000 for this parameter. And you can see that at the beginning of the simulation, we initialize this parameter such that we have a fairly wide sampling distribution, but that quickly becomes narrowed and then starts to follow the path of increasing probability. And so you can see that as we initially started the simulation, we found some local minimum, and we're approaching that local minimum, and then sat here in this local minimum for a little while, maybe about 1,000 iterations. And then we started to travel along of increasing probability space, and then find this new local minimum. And we can actually see this kink in this change in the parameter value here, and that syncs up with the increase in log probability on our plot. Okay. Yeah, so now we can actually look and see now after this 2,000 iterations what our best phase diagram actually looks like. And so so if we go ahead and plot this up, we can see that after these 2,000 iterations, we have a phase diagram that's in very good agreement now with the phase boundary data. But if we go, and I didn't have this set up, but we can quickly plot also the new thermochemical data as well. And so we can look at dBF MC or dBF start should be what we started at. And then after the 2,000 iterations, we can also plot the same thing and see what we get. Just can't spell. Yeah. Okay. So now now we can see here that again, if we're looking at BCC, we increase the stability again of BCC compared to the initial starting point, and we can of course do this analysis for every phase that we want it to do. All we have to do is change the phase name. So if we look at FCC before and after, we can see here's the before, where we're sort of going through straight through these points in the middle, and we're expecting that it's a little more stable on this side. But then as we go through the simulations, going through the MCMC simulations, we can see that we adjusted the stability on the chrome side to make FCC a little more stable, and also a little more stable on the nickel-rich side as well. And so again, just for the sake of time, I don't want to talk about these challenges here, but before we wrap up with MCMC and I show a little bit of results about the uncertainty quantification, is there any other questions that haven't been addressed in the chat yet that people have? Okay, I see a new one in the chat about using Anaconda. You have a problem where you see this failed with initial frozen solve, and it takes a while. That's normal. We ship PyCalFed in 2 different Anaconda channels, and so by default it tries to get everything but from one channel, but we don't have all the dependencies in both of them, and so it will fail initially, and then it should succeed on the second try, maybe third, depending on what you have installed.
And so one thing that you can do also is sometimes if you're trying to install PyCalFed and ESPEI into an existing Conda environment, it will fail. We've had some users report failures on that, but you can install PyCalFed and ESPEI into their own environments. So you would use Conda create instead of Conda install, and you would just specify a new environment. And that usually speeds up the dependency solving and sometimes can work around failures if you've encountered failures.
Thank you.
Yeah, thanks, Richard. I can give maybe 30 more seconds if anybody has any questions, and then I'll move to show some of the UQ results and what you can do after you run these MCMC simulations. Okay. If there's no more questions, then I can show these last few slides here. So again, now we've done this this optimization here. So again, we have this like copper magnesium phase diagram where we've done these MCMC simulations and we've quantified the uncertainty and created these Markov chains for all our parameters. But now what do we do with those? And so the obvious answer that I've alluded to is now we actually do the uncertainty quantification and start to take our parameter uncertainties and propagate those through to through different properties that we can calculate. And so basically, if you're not familiar, the way that this works is that we have these CalFed parameters. So like I mentioned, we have this VV0001, which is the parameter for this CalFed type parameter. And then we've taken a bunch of samples of that parameter. So again, each of these lines corresponds to one chain, and we've evaluated that chain for a certain number of iterations. And so every iteration and chain combination is one sample of that parameter value. And so then all you do to compute the uncertainty and propagate that forward is you go ahead and calculate, you forward calculate all the different combinations of parameters into the property that you're interested in. And so you can also do subsets of them. So maybe you don't want to look at the entire probability distribution, but you only want to look at the 95 highest density interval, or so the 95% of your samples that have the highest likelihood, or maybe you want to only look at the 50% highest likelihood samples. You can do all that as well. And so just as an example of what this looks like, so here are several different parameters for the enthalpy of mixing. And so we've propagated through the parameter samples to these parameters, but then we of course go and combine them all and sum them as typical. And then you can propagate these different parameter uncertainties into uncertainties for properties. And so this is a very simple example, but really the power in this is that you can do this for anything that you can calculate in PyCalFed. And so I have a couple examples here that we talked about in our 2019 paper in Actimap, where we've propagated the uncertainties. These are all in copper magnesium. We've propagated the uncertainties for the Gibbs energy of FCC and liquid. And so we can see in this example that the FCC is much more uncertain than the liquid. And we see that actually throughout all of these, that the FCC is more uncertain, which again should not be surprising if we look back at the phase diagram from a couple slides ago, just given how few data there are that describe this FCC phase on the copper-rich side compared to how much data is available for the liquid. It's no surprise that the liquid is much more certain relative to FCC. And so here on the right, we've plotted the relative phase boundaries for the metastable FCC liquid. And so we can see on the left, relative to the right, we're much more certain about where these phase boundaries are compared to the magnesium-rich side where FCC is metastable, and we don't have any experimental information to access those. We have very little certainty about where these phase boundaries are. And I didn't mention the way we do this for something like a phase diagram is the same way we do every other property. So we calculate where the phase boundaries are, and then we just stack them all on top of each other, which is the exact same thing that we do for any other property. So we compute the phase fraction versus temperature of these phases at a particular composition, and then we've stacked all those different parameter, all the different properties that we calculated for different parameter sets on top of each other, and just delineated the minimum and maximum in this case with these shaded regions. And then we can also calculate, like I said, any other property that you can imagine. So we can calculate here what the probability of observing the liquid phase is on the phase diagram. And so again, we're fairly certain along this FCC edge, but as we go into this, again, metastable region where FCC is metastable, we have some range and probability. So these are really the same figure, just shown different ways. And so again, just to sort of put it together, here's the stacked up, all of the phase boundaries, the zero phase fraction lines stacked up for all the different parameters that we selected in copper magnesium. And so all these figures are part of this PDUC package. So Zique mentioned this earlier. So this one is led by Noah Paulson and Marius Stan at Argonne National Lab. And so again, this is a case where people are finding ESPEI useful to include in their work, and have even started to derive these analysis post-processing packages around it. And then I also wanted to mention some further work, again, that Zique mentioned earlier, about sensitivity estimation for different CalFed parameters and that we can do with ESPEI. And so sensitivity, the simple conceptual way to think about it is it's just the derivative of the likelihood with respect to the parameters. And you can do all kinds of really powerful things in that. So in this paper, we developed both the mathematics for evaluating the sensitivity and and showed some test cases on this chrome nickel system. And so here are just two results I wanted to highlight, where we've looked at all the different CalFed parameters. So again, these are the A plus BT coefficients for different CalFed parameters. You'll have to excuse the different naming convention, but we've plotted the sensitivity here as a function of the number of iterations, and we can see that initially, as we're first starting our simulations, the most sensitive parameters is this dotted dash line. So this L0 liquid A, which maybe isn't surprising because we have that wealth of data for the liquid, and so a small change in the parameter gives a large change in the total likelihood. So again, that's what our sensitivity is a measure of, is how much a change in a parameter affects the change in the likelihood. But after some time, what we're seeing here is that the liquid begins to be less and less sensitive compared to other parameters. So as we start to converge the liquid, perhaps we start to find that the parameters controlling the FCC stability, so this L1, this L1 A term in the excess parameter is dominating there. And so again, there's more detail and explanation in the paper, but I wanted to give a preview of these. And we also have we can also look at sensitivity for individual data sets. again, all described in the paper. But there's some really interesting and important conclusions on from what we can draw from looking at these sensitivities. I also see a question in the chat about whether we took into account the uncertainty in the chromium melting point. So in this paper and in this analysis, we did not look into that. But you could, in principle, if that were of interest to anyone to investigate that, you could absolutely use ESPEI to do that. So as I mentioned before, you can control which parameters are degrees of freedom by giving them a name like VV and some number. And so you can add those in for the chrome unary and treat the chrome unary as a degrees of freedom, and then optimize those to the data that's available for the chromium melting point, for example, as well as all the chromium thermochemical data for the solid phases and the liquid phase. And you could inform yourself on the uncertainty and also the sensitivity as well. And yeah, so again, this was the phase diagram that we got at the end, and I just wanted to close then, as we're getting close to time here, by thanking all the other organizers who made this workshop happen. So Richard, myself, and Zique on behalf of the Materials Genome Foundation, and then Jan, Tillman, and Jorg on behalf of the Max Planck Institute for Iron Research. So again, I just want to thank you all for your time, and I'll take any questions and open up the discussion at this time.
I want to just thank Brandon and Richard for the wonderful presentation. Thank you for your excellent hard work. And by the way, Brandon is finishing his PhD. If anybody needs to hire somebody, and and Richard also, basically what I could put is that Richard finished his PhD with PyCalFed, started the ESPEI, and Brandon finished his PhD with ESPEI. So I hope they carry forward, as I've seen Richard has been carried forward for the last 4 years now. And I hope Brandon will continue to carry it forward for, well, many years to come. Thank you very much. It's highly appreciated.